Hey everybody, it's Dan from sagemathtutoring.com, and got a couple problems here, 4 problems actually, that my student is working on, and I want to go over them. And they have to do with quadratic functions and how to graph them without a calculator, how to get a sense of what the graphs look like. And actually, these quadratic functions are going to be in both vertex form and in general form. Sometimes some would call vertex form standard form, but I'm just going to refer to it as vertex form. And there's some slight differences with regards to how you need to approach quadratic functions that are in vertex form and how you need to approach quadratic functions that are in general form. And the 4 problems that we're about to go over sort of cover that fairly well. So anyway, let's begin with this problem right here. We've got negative 3 times x minus 4 squared minus 6. My student correctly recognized that the graph opens down. And the way that we know that is because of the negative 3. The 3 happens to be a negative. Sometimes it's helpful to think of the function in vertex form as the following. And by the way, this is vertex form. So the function would be something like this, where if a is negative, then the parabola opens downward. If a is positive, then the parabola opens upward. So that's important to remember. All right. My student also correctly recognized that there are some transformations. This parabola does go right 4 units, down 6 units, and has a stretch of 3. So how do we know that it goes right 4 units? Well, that's because of h. And I'll actually rewrite this as the actual equation that we are dealing with. So basically, we know that it goes right to the 4 because this tells you, h tells you how many units to the right or left it goes. And when it comes to horizontal translations, it's often useful to just imagine the sort of opposite of what you would think the transformation would be here. If it says x minus 4, one might think that that means going 4 units to the left, but in reality, that means that you're going 4 units to the right. My student also correctly recognized that there is a vertical transformation or translation downward 6 units, and that's due to this. The k will tell you how many units down the parabola goes. All right, so, or up. In this case, it's down because of the negative in front of the 6 right there. So when it comes to horizontal translations, it might be counterintuitive with regards to which direction you think it's going to move, right or left. When it comes to vertical translations, it's actually intuitive in that if it says minus 6, that means it's going down 6. All right, so determine the coordinate of the vertex. Well, that would definitely be hk. The vertex is always going to be hk, and in this case, the h is the number being subtracted from x right now, which is 4, so we could even write that. And the k is the number that is being, we could say, currently added to this term. And the number that's being currently added to this term, in this case, is a negative 6 is being currently added to this term. So that's a way of thinking about it. Now, another way of thinking about getting clear on the vertex, and this is all vertex stuff right here. Another way of getting clear on the vertex is, once again, to think of the h, associating the h as that which is counterintuitive. So if there's a negative 4 in here, that means it's going to be a positive 4 here. And you can think of the k as, or associate the k with that which is intuitive. Over here, if it's a negative 6, well, then it's just a negative 6. So this first term will always kind of correspond with the opposite of what you would think it would be. All right, so that's something to keep in mind that might be helpful. Okay, so let's see. Determine the coordinate of the vertex. We just did that. Determine the coordinates of the Y-intercept. Well, my student, I don't even have to do this because my student actually did this correctly right here, which is great. So, and when I say right here, what I mean by that is in the image. So if you look at the image, what my student did is he replaced x with 0, and then he just found out what you would get as a result of substituting 0 in for x. And it turns out that we do indeed get a negative 54 in that case. I'd also like to draw attention to the fact that my student did a great job using PEMDAS, right? PEMDAS says you got to work with what's inside parentheses before you move on. And my student did that. My student simplified everything that's inside these parentheses first, and it became a negative 4. And then according to PEMDAS, it says you got to do exponents after that. It's the E in PEMDAS. So that means apply this 2 to the negative 4 next. And that's what my student did. Negative 4 squared is definitely positive 16. So we ended up right here. And then my student went to M in PEMDAS, which stands for multiplication. It was a negative 3 times a positive 16, which ended up becoming negative 48 minus 6. And that does indeed become negative 54. So that's correct. My student did a great job with that. Find the solutions of the function. That's the next part. So, okay, this is the first time that we have a departure from what you would do when this function is written in general form. If this function was written in general form, then we would want to probably just rely on the quadratic formula in order to find the solutions. Since this function is written in vertex form, you might want to rely on what some math teachers would call the square root method. We're actually going to do that down here. So let's see, get a little bit thinner ink here. And what do I mean by that? Well, basically, what you want to do here, if you want to find the solutions, that is in essence saying set y equal to 0 and solve for x. All right, that is in essence what they're saying when they want the solution. So if you set y equal to 0, you're going to have this, obviously. And if we want to solve for x right there, I mean, it would be nice if we could get at least this whole term by itself, right? And then you could ask yourself, well, what's in the way of this whole term being by itself? Clearly this negative 6 is in the way, so we got to get rid of that negative 6 by adding 6 to both sides. That would result in the following, where we have we'll just do a nice arrow over here. We would have 6 equals negative 3 times x minus 4 squared. So once again, we want to solve for this x right here. So wouldn't it be nice if we could at least get this x minus 4 squared by itself first? We're kind of whittling things down. And the answer is yes, it would be nice. And the thing that's in the way of this being completely by itself is clearly this negative 3. So we got to get rid of that negative 3. We could do that by dividing both sides by negative 3. And then you would end up with, negative 2 equals x minus 4 squared. And in order to solve for x, it would be nice if we could at least have x minus 4 completely by itself. But the thing that's in the way of x minus 4 being completely by itself is this exponent of 2. And the way to get rid of that is to take the square root of both sides. And when you do it on this side, you definitely need to do the plus minus thing over here. When you take the square root of both sides, always be in the habit of going plus minus on the other side. All right. Now, of course, this would result in x minus 4 being completely by itself. But if you notice what we have going on right here, you should have like a red flag go off in your mind, in that we have the square root of a negative number, which basically means that there would be an imaginary number here. Now, when you're dealing with these parabolas and you're trying to figure out what the solutions are and so on, basically, if you end up taking the square root of a negative number, that means that there are no real solutions, which basically means there are no X-intercepts at all. You know, maybe this parabola is like this or something like that, where it's pointing down actually doesn't cross the x-axis at all, and therefore, since it doesn't cross the x-axis, there are no x-intercepts there. So that's something to take into account. So we could actually stop in this moment, because they're like, find the solutions of the function. Well, basically, there aren't any real solutions. So the answer could be that there aren't any. So I'll write that in blue. I'll say there are none. All right, I think that should suffice. And let's see. Determine the coordinates of the x-intercepts. Well, guess what? If there's no real solutions, there's no x-intercepts. Because what's a solution? The solution of the function is the x values, or we could say the x values where the parabola intercepts the x-axis, right? So if you have a parabola like that, the solutions would be the x values where the parabola intercepts or intersects the x-axis. And if there aren't any solutions, guess what? There are no x-intercepts. So I'll just say not applicable. Determine the equation of the axis of symmetry. Well, that's always very easy once you have the vertex. And we already have the vertex, actually. We had written that before. In this case, it is 4, -6. And once you have the vertex, finding the axis of symmetry is very easy. That will always, always, always just be x equals whatever the x-coordinate is of the x-intercept. In this case, of course, it is 4. Determine the domain. So my student by now knows that the domain for all of these types of problems by now is always going to be -infinity, +infinity. And that's because, parabolas do not just open upward forever. They also open outward forever, which basically means that every single x value will be represented somewhere on the parabola. So that is going to be the case with all of these problems, if you're dealing with parabolic functions at least, and it's not like a piecewise situation or there aren't strange parameters involved. Determine the range. I had advised my student, in my opinion, correctly in the last video and during the session. At this point, even though the next question says graph the parabola on the coordinate plane given above, we're supposed to graph it here. But I would say just let's go ahead and graph it now, because actually graphing it would help you find the range by just kind of visually looking at it. And I'm going to assume the teacher doesn't mind that we would rely on the sort of visual at this stage in the game. So determining the range, well, let's get an idea of what the graph might look like. Obviously, we have the vertex at 4, -6. So that is going to be, let's take a look, over 4. And then down 6. 1, 2, 3, 4, 5, 6. That's going to be right here. Okay. We also know that this parabola is going to be opening downward. And we also know that it has a stretch of 3. Now, we don't really need to worry about the right 4 down 6, because that part was already taken care of with the vertex. In fact, the vertex kind of tells us that it goes to the right 4 and down 6. It's kind of embedded within the vertex. One thing we do need to take into account, though, is the fact that it opens down and the fact that it is a stretch of 3. Now, there's a couple ways you could go about this, but here's the way that I would suggest. If it's a stretch of 3, that means that this thing is narrower than it typically would be. Now, in order to understand the stretch of 3, let's get an idea of what this thing would look like under so-called normal circumstances. Under normal circumstance, if there was not a stretch or shrink, you would have a parabola pointing downward. Therefore, you would have these points right here, because it's helpful to sort of consider, when dealing with a normal parabola, this relationship of these two boxes right here, where the vertex is here, and then we got a corner of a square. The next point is at this corner of the square, and then the next point over here is at this corner of this square, right? So it's helpful to sort of remember that configuration, because it'll help you with a lot of these stretches and shrinkings. Now, we're not dealing with that situation. What we are dealing with is a parabola that has a stretch of 3, which basically means we would take what used to be a point here and a point here, and we're stretching it in this direction downward. So instead of going over 1, down 1, it's going to be over 1, down 3. All right? So the point's going to be there instead. And what I'd rather do, actually, is get a different color. So it's going to be this relationship right here and this relationship right here. Now you could sort of liken this to a slope of a line, especially when you're looking at this rectangle right here. Not so much this rectangle, but when you're looking at this rectangle right here, you can sort of liken it to the slope of a line, because, you know, what is the equation of this parabola? It's this, right? And you could sort of think of this -3 as the quote-unquote slope, as a temporary concept in your mind. And what does that slope say? Well, slope is always secretly a fraction. So we have the fraction of -3 over 1. Well, -3 is the rise, and +1 is the run. So one way of going is you could take a look at whenever you're graphing these parabolas, take a look at the rectangle on the right, and just think of going down 3 over 1, and that tells you where to put your next point. And of course, if you draw a point here, you could match it over here. So that will satisfy the stretching action. And we're going to write that stretch right now. We're actually going to graph this thing right now. So it looks something like that, and that's kind of ugly looking, but you get the idea. So the range would be the set of all y values that are represented on this graph, and that is clearly going to be all of this stuff, right? And what we could see here is that the range would be -infinity all the way up to -6. Now notice how when it comes to this interval notation, you always want the lesser of the two numbers to be on the left and the greater of the two numbers to be on the right. Now, there is no number that is lesser than -infinity. So if you end up with a -infinity within your interval, I'm going to tell you right now, that's always going to go on the left. All right, so that could be something that a lot of students might get thrown off by. They might actually make the mistake of putting -6 first and then -infinity, because maybe they just associate infinity with big and therefore large. But remember, -infinity is infinitely small, and the smaller of the two numbers, the lesser of the two numbers, would go on the left. All right, so that is the range of this graph. And we'll write that here. That's all good. So it was -infinity, -6. And then we're done because we already graphed it. Smiley face. All right, moving on to the next. So this graph, or this function I should say, is written in general form for x squared minus 4x plus 1. It's not in vertex form, so we're going to have to kind of use some different moves here. But analyzing it nonetheless, as we can see, my student correctly answered this question: does the graph open up or down? Well, it opens up. How do we know? Because the same rule that applied to the last function applies to this function, in that when this leading coefficient is positive, that means that the graph opens upward. If it's negative, that means that the graph opens downward. My student's really good at that stuff, so we got the correct answer there. Now, determining the coordinate of the vertex, well, in this case of the general form, you're going to want to use this whole thing where you use negative b over 2a. That will give you the x coordinate of the vertex, and you want to just start there. Now, I would advise, I'm kind of religious about this, I would advise rewriting negative b over 2a as negative empty parentheses all over 2 times empty parentheses. All right? Because you want to be really careful when it comes to substituting in these numbers. And let's get clear. First of all, a is positive 4, b is negative 4, and c is 1. And when I substitute my negative b in there, you want to be really careful. You want to actually put in b, right? And b we just established is negative 4. And you want to be really careful here. You want to make sure that you put a inside the parentheses, and a is positive 4. Now, some of y'all are sort of picking up on why the parentheses are good. The parentheses are good because when you draw the parentheses first and then plug the number in, you could very, very clearly see there's no mistaking that this is a negative, right? And this double negative scenario would give us a positive 4 up top, and that would be all over 8, which, by the way, equals 1/2. So that would be at least the x-coordinate of the vertex. Now we're going to find the y-coordinate of the vertex. Now, the way to do that, you could do this in your calculator if need be, but the way that you do that is to find out what g of 1/2 is. In other words, substitute 1/2 in for x, and then proceed from there. Now, this is something you could do in your calculator. If you did want to do it in your calculator, always use PEMDAS, figure out what this is first if you don't have a graphing calculator. If you have a big fancy graphing calculator, you might be able to plug this whole thing in and just press enter or equals or whatever, and it'll pump out the answer. But regardless, I'm actually going to pause the video right now and come up with the answer, and I will just write it down. Okay, so if we were to calculate all of this, this would become 0. So what does that mean for us? That means that the vertex is at 1/2, 0. So I'm going to write sort of an obnoxious arrow right here, and we're going to write that vertex right here. 1/2, 0. That's the vertex. All right, so moving on. Determine the coordinate of the y-intercept. Well, when it comes to these general form / parabolic functions, the y-intercept is actually very easy to figure out. All you have to do is substitute 0 in for x, and in this case, that would be the following. And actually, that's what you would have to do with the vertex form as well. But I guess the reason why I'm saying it's easy is because it's really easy to calculate this almost just by looking at it. You can see that's 0, so therefore we would be left with 1, right? At a certain point, you might even be able to get in the habit of just being like, oh, the y-intercept? Well, when the graph is written in general form, the y-intercept is always going to be this. When it's in general form. Not when it's in vertex form, but when it's in this general form, the y-intercept is always going to be that. So that's something to keep in mind. And we just properly figured out what the y-intercept was. Not sure why that didn't connect, but we're going to connect it right now. All right, so find the solutions of the function. All right, so finding the solutions of the function. Now, before, when we found the solutions of the function when it was in vertex form, we used the square root method. We set y, we could call this y. We set it equal to 0, and then we solved using the square root method. However, in this case, when we find the solutions of the function, since it's written in general form, I would advise just simply relying on the quadratic formula. And as a quick reminder, the quadratic formula is this. That's basically where it's like x equals negative b plus minus b squared minus 4ac. You know, you might even want to just write it before you do it. So that's the quadratic formula. Now we're going to use it. And similar to what we did before, I'm going to strongly advise using empty parentheses. So, empty parentheses. Before I worry about what belongs inside these empty parentheses. All right, so what does go inside these empty parentheses? Well, clearly it would be, you know, A, B, and C. We're going to plug all that in, and I'm going to do that right now. So A is 4, B is negative 4, and C is 1. So let's take a look. So, therefore, negative 4 would go here. It would also go here. A is positive 4, so that would go here. That would go here, and C is 1, so that would go here. And working this out, let's be meticulous about this. We have x equals negative 4 is just 4, plus minus, let's see, so that'd be 16 minus 16, which is 0, and that is actually very good news. We have a 0 underneath there, all over, clearly 2 times 4, which is 8. Now, this is sort of an unusual looking situation. It's probably the case that most students are not used to having 0 underneath here. But good news, radical 0, the square root of 0, is just 0, because 0 times 0 equals 0, right? So the square root of 0 is 0. So what that means is we could actually rewrite it. I'll do it an arrow over here. We could rewrite this whole thing as x equals 4 plus minus 0. But do we really have to write plus minus 0? No, we don't have to write that, because 4 plus 0 is just 4. 4 minus 0 is just 4. So good news, we don't have to write that. But we still want to keep the denominator, which is 8, and then that, of course, equals 1/2. Notice how this is the only solution. It's often the case that when the teacher asks for solutions, there's usually going to be more than one. But every now and then, you're going to get some weird situations. You're going to get a situation where it's like, there are no real solutions, which is what we just dealt with last time. And you might also get a situation where there is actually just one solution. Okay? Now, let's get very clear. What does a solution mean? A solution is a place on the, is the value or values on the x-axis that the parabola hits when it intercepts the x-axis. So in this case, the parabola is only hitting at one point, namely 1/2, which tells me that the parabola swoops down and just lightly grazes 1/2 and then goes back up. So it literally intersects the x-axis at only one point, namely the x value of 1/2 and also the y coordinate of 0, which we're going to get to right now, because the next question says, determine the coordinates of the x-intercepts. Notice the s in parentheses, which implies that it could just be a single x-intercept, which is what we're dealing with, because we only have one solution, right? Find the solutions. We found one solution. And the solution will always be the x-coordinate of the x-intercept. And by the way, what will the y-coordinate be of the x-intercept? Well, basically, the y-coordinate of any x-intercept will always be 0. I'll write that in some blue ink. It will always be 0. Why is that? Well, let's analyze a couple points on the x-axis. Let's say we had an x-intercept here and here. Well, you'll notice that what these points have in common, this point has the coordinates of, -6, 0. This point has the coordinates of -2, 0. Clearly, you can see what they both have in common is that y-coordinate of 0. So in other words, any point on the x-axis is going to have a y-coordinate of 0. And that's why anytime you intercept the x-axis, that point of intersection will have a y-coordinate of 0, which is why this y-coordinate is 0. We could put that every single time. As long as there's an x-intercept, there will indeed be a y-coordinate of 0 at that x-intercept. Even if there's two x-intercepts, the y-coordinate will be 0. So that's something to keep in mind also. So let's see. The next thing we want to look at is, determining the domain. Yeah, sometimes it doesn't stick. I'm not really sure why. We'll just put the 0 there. Hopefully it sticks this time. All right. Okay, determine the axis of symmetry. So once again, once you have the vertex, this should be easy. It's going to be x equals whatever the x-intercept of the vertex, or the x-coordinate is of the vertex. And in this case, it would be 1/2. All right. Axis of symmetry, I said in the last video, is the invisible dotted line that cuts up through the vertex of the parabola. Determine the domain. My student definitely knows that this would be -infinity, +infinity. Determine the range. So now, when we determine the range, I'm going to once again advise graphing this thing first. So we do have enough information to graph this. The vertex is at 1/2, 0, so we're going to graph that first. Here is 1/2, 0. And what else do we have going on? Let's see. We know that it opens up, and we also know that, interestingly, this one didn't ask for any transformations. The last problem asked for transformations. This one doesn't. But what we do have is a is 4. So once again, I would suggest to my student to kind of temporarily treat this as though it's the slope. So number one, get clear that it's going up, right? So if it's going up and a is 4, that means that we're going to take into account the fact that a is 4, which, by the way, that's really 4/1, right? And if we're going to treat that as the slope, this is the rise and this is the run. So that means that this thing goes up 4 and over 1. It's a rise of 4, so it goes 1, 2, 3, 4, and then over 1, which lands us on this point right here. Okay, similarly, we could go up 4 and then over 1 in this direction, and that lands us on this point. So that's something that we could do if we want to take into account the stretch, and then from there you could just kind of graph it. Now once again, I'd like to highlight the fact that this vertex is resting on the x-axis, which is why there is only one x-intercept. It's right here. The x-intercept is the vertex. This is the only place where this parabola crosses the x-axis, is right here. So that's that. Once you've graphed it, it's fairly easy to determine the range. The range is the set of all y values that's represented on this graph, and that would be all of these guys, right? That's the range. Now clearly we can see it goes from the y value of 0 upward. So the upward part means positive infinity, and 0 is included, so it goes from 0 to positive infinity. Notice how, once again, the lesser of the two numbers is on the left and the greater of the two numbers is on the right. All right, graph the parabola on the coordinate plane given above. We just did that. All right. So anyway, that is this problem. Okay, so moving on to the next one. What do we have? What do we have? We have, does the graph open up or down? Well, we know, I probably should have done this last time. I'm going to do it this time. A equals -2. I did do it last time, but I didn't do it right away. So we're going to get clear on A, B, and C right now. All right, so since A is negative, that means it opens down. So my student did a good job with that. We're going to determine the coordinate of the vertex. Well, this is written in general form. My student definitely knows that that means we're going to do this -b over 2a stuff. Once again, I would suggest doing the empty parentheses and putting in, your b now. So b is 5 and a is -2. Now, once again, the point of empty parentheses first is because we want to be careful with the negatives. Clearly, this is a 2 times a -2. So you want to not make mistakes with regards to the signs. This becomes -5 all over -4, which becomes positive 1.25. That's the x-coordinate of the vertex. And in order to figure out what the y-coordinate is of the vertex, you absolutely must find what f of 1.25 is. In other words, plug in 1.25 into the function. In other words, substitute 1.25 in for x. And that's what we're going to do right now. I'm going to do it in a darker color. I'm actually just going to do it in black because that green's a little hard to see. So this is what you would calculate in order to figure out what the y-coordinate is. Looks like we're having trouble here. Let's see. I'm going to get thinner ink. So this might be very thin, but hopefully y'all can see it. Empty parentheses plus 5 times an empty parentheses minus 3, and 1.25 is going to go inside these parentheses. 25, 1.25. So that is the calculation that we're going to need to perform. Now this is annoying because it's like 1.25 squared and then 5 times 1.25. This is a decent thing to do in your calculator. Once again, if you're using the calculator, do PEMDAS. So in the absence of a fancy graphing calculator, you will actually have to figure out what 1.25 squared is first and then multiply -2 times whatever you get. All right. I'm going to pause the video and actually do the calculation right now, and I'm going to write it right here. Okay, so what I discovered upon doing all these calculations was that f of 1.25 ends up equaling 0.125. So what that means is, let's recap this. We want to find the coordinate of the vertex. First, we did -b over 2a in order to get the x-coordinate of the vertex, and that ended up giving us 1.25. Then to find the y-coordinate of the vertex, we plugged in 1.25 into the function. In other words, we found out what f of 1.25 was. How did we do that? Well, we substituted 1.25 in for x, and then that gave us 0.125. So at the end of the day, the vertex is the following. It is 1.25. Yeah, it's not big enough. The vertex is such that I am going to write it elsewhere because I don't have enough room right here. So I'm going to write the vertex down here. The vertex is 1.25 times 0.125. All right, so that's the vertex. And we could just kind of keep in mind that it's down there. Okay, determine the coordinates of the y-intercept. Now, before I had talked about how when you want to find the coordinate of the y-intercept, the y-intercept's really easy to figure out. It's just this number over here when the function is written in general form. So it is -3. Bam. Now, by the way, if the teacher wants the coordinates of the y-intercept, well, that would be 0, -3, because when it comes to the y-intercept, the x-coordinate will always, always, always be 0. So that's that. Find the solutions of the function. Once again, that is to use the quadratic formula. And why are we using the quadratic formula to find the solution to the function? It's because this function is written in general form, and the quadratic formula is a safe bet. Quadratic formula is kind of clunky and ugly looking and all of that, but it is, I suppose it has a certain beauty to it. Maybe there's an elegance to it from a certain perspective, but you know, the one thing that's really great about the quadratic formula is that it always works. It's the kind of like go-to default. You know, sometimes you're not going to be able to factor quadratic equations and solve them like that. Sometimes, you know, it's not going to work that well for you. You could complete this square, though. That's something you could always do, too. But quadratic formula, once you have it memorized, it's pretty straightforward. So we're going to substitute in the values that belong here. We got 5, we got 5, we've got -2 right there, we've got -3 right there, and we got -2. And I'm going to pause the video and do this calculation also. So after performing this calculation in my calculator, I ended up getting that x equals 1 and 1.5. So basically, when it is -5, when it's -5 plus this thing all over -4, you get 1. And when it is -1 minus all of this stuff, then you end up, and divided by -4, then you end up with 1.5. All right, so those are the solutions. And then they ask you, determine the coordinates of the x-intercepts. Well, the x-coordinates of the x-intercepts will always be the solutions. So we have 1, and we have 1.5, and the y-coordinates of the x-intercepts will always be 0. Done. Determine the equation of the axis of symmetry. Once again, as long as you have the vertex, this will always be easy because this number will always be the x-coordinate of the vertex. And our vertex is written down here. It's kind of hard to see. But the x-coordinate, as you may recall, is 1.25. That's also written right here. The x-coordinate of the vertex is 1.25. So that's all we need to know for that. My student definitely knows that the domain is this. And as far as the range goes, I would graph this thing immediately just to get an idea of what the range is. So the vertex is 1.25 comma 0.125. That is a crazy vertex, but you know what? We're going to sort of approximate it. I mean, this is 1, so 1.25 is going to be like right around here. 0.125 is up just like a little bit right there. All right. And what else do we have to contend with? Yeah, we know that it opens down, and we also know what the X-intercepts are. The X-intercepts are 1, 0 and 1.5, 0. So those would be 2 good points to graph. So 1, 0 is clearly right here. And what was it again? 1.5, 0. Yes. Thank God for this zoom in feature, because 1.5, 0 is like right here. So as you can see, it's very, very tight, right? And then we also know what the Y-intercept is. It's 0, -3. So that's something that we could also graph as well. That would be right here. Now, since the axis of symmetry is like like that, that means that this should be symmetrical with that, which means that there should be another point right there. So you could kind of piece it together in this way. And in my opinion, 5 points most definitely is sufficient to graph this thing, right? That's an ugly looking parabola, but you get the idea. So the reason we're graphing it is partly because they want us to graph it in the last section. However, in this section, we just want to find the range, and that is the set of all y values that are represented on this parabola. And basically, that is all of these. You know, what's going on? Well, it's definitely going to be negative infinity because it goes down forever. So negative infinity is in the range. But what's the highest y value? The highest y value is this right here, whatever this y value is. Well, that would be the y coordinate of the vertex, right? And we already established, you know, we'll write the coordinates of the vertex. The coordinates of the vertex are 1.25, comma, 0.125. And that right there is the y-coordinate of the vertex, also known as the highest point of the graph. And by the way, quick preview, mathematicians call that the maximum. All right, so our range, without question, goes from negative infinity all the way up to 0.125. That's it. And then we already did this as well. So that's that one. All right, so we got the final problem right here. And we've got 2x squared plus 6x plus 5. Obviously, this is written in general form. And you know what? Before we begin, let's get clear. We got a equals 2, b equals 6, and c equals 5. Graph definitely opens up for sure because a is positive. And determining the coordinates of the vertex, since it's in general form, we will have to do it this way. So once again, using the empty parentheses. In this case, b is 6, a is 2, and of course this would result in negative 6 over 4, and that reduces to negative 3/2, and we could sort of keep in mind that that is definitely going to be negative 1.5. That might come into play later. And in fact, it might come into play right now, now that I'm thinking about it, because we're about to plug that in to the function, right? I'd rather sort of think of it as that decimal. So we've got negative 1.5 equals, and we'll kind of blow this up a little bit. So it's 2x squared plus 6x plus 5. So I'm going to write empty parentheses again. So instead of 2x squared, I'm going to write 2 empty parentheses squared plus 6 times empty parentheses plus 5. And what goes inside those parentheses? Well, that would be negative 1.5. So negative 1.5 here and negative 1.5 here. So I'm going to pause the video and make this calculation in my calculator right now. Alright, so after doing that calculation, what I came to see is that f of negative 1.5 equals 0.5. So once again, I'm going to sort of use the star because we often run out of room once we do this part. Before I sort of finish the star though, let's get clear. This is the x-coordinate of the vertex, negative 3/2, also known as negative 1.5. And this right here, I'll do this in green as well. This is the y-coordinate of the vertex. And we're using a star to denote the fact that the vertex is sort of written down here. It's like stashed down here. And that's just because we need to save the room. So that's the vertex, and we could use that later. So moving on, determine the coordinates of the y-intercept. Well, by now, the y-intercept, we should know by now that the y-intercept is definitely going to be 5. And the reason is because of this 5 right here. The best way, the kind of foolproof way to find the coordinate of the y-intercept, or the y-intercept in general, is to just set x equal to 0. We could easily see that if x was 0, this whole term would become 0, this whole term would become 0, and it would leave us with 5. So that's why the y-intercept is 5. Now, again, if the teacher wants you to write the coordinates of the y-intercept, you might want to write down 0, 5, because the x-coordinate of any y-intercept is going to be 0. And the reason is because, of course, any y-intercept would be a point on the y-axis, and all of the points on the y-axis have an x-coordinate of 0. So that's that. Okay, find the solutions of the function. Well, when it's written in general form, 2x squared plus 6x plus 5, you might want to use the quadratic formula. And the quadratic formula is the following. We'll make this a little bit bigger. Negative b plus minus b squared minus 4ac all over 2a, and then we have negative, or equals, negative empty parentheses plus minus radical empty parentheses 4ac all over 2 empty parentheses, and then you just plug it in with what you know a, b, and c is. A is 2, B is 6, and C is 5. So I'll jump in here. 265. So this is 6, this is 6, this is 2, this is 2, and this right here is 5. And I'll pause the video right now as I perform this calculation. So after looking at this calculation, I came to see that it would be an imaginary number right here, because 6 squared is 36, and it would be subtracting, it looks like 40 over here from that 36, and that would give us a -4 underneath the radical. And anytime you have a negative number underneath the radical, that is an imaginary number. And anytime you have an imaginary number in your solutions of a function, that means that there's no real solutions. And basically what that means is this parabola does not intercept the x-axis. That's what it means. And it's kind of good news when this happens, because the moment you find out that you have a negative number underneath this radical, well, that's the moment that you can just stop, because the teacher asks you to find the solutions of the function. Well, there aren't any solutions. Done. Moving on to the next, determine the coordinates of the x-intercepts. Well, if there's no solutions, because there's an imaginary number right here, well, there's no x-intercepts, because what are solutions? Solutions are the x-coordinates of the x-intercepts. If there's no solutions, then there's no x-coordinates of the x-intercepts, and therefore there are no x-intercepts. So I believe the teacher should be happy with you just saying there are none. All right, moving on. Determine the equation of the axis of symmetry. Well, that has everything to do with the vertex, which is down here. And the equation of the axis of symmetry will always be x equals whatever the x-coordinate of the vertex is. In this case, it would be -1.5. So that is the equation of the axis of symmetry. Find the domain. As my student knows, this would be the following. And determine the range. Once again, we might want to graph this thing first. Now, it's a good idea to get clear on the vertex. That would be -1.5 and +0.5. So we're going to jump in here and take a look at -1.5. Well, that would be right here, and +0.5 would be right here. So we're going to put a dot right there. And what else do we know about this graph? Well, we know that it opens up, and that makes sense because it says that there's no real solutions, which means that this parabola, whatever it looks like, it should not cross the x-axis. So the fact that it goes up from here is a good sign. What I would do is focus now on the y-intercept. Now the y-intercept is this. It is 0, 5, so it makes sense to plot a point there as well. So let's see, 1, 2, 3, 4, 5, right there. And anything that you plot over here, because there is that axis of symmetry that goes up vertically through this vertex, it makes sense to mirror this point over here also, because of symmetry. And in case that's not clear, at least the way my mind works, I literally imagine sort of this like rectangle, a shape right there, where this blue vertex is at one corner of the rectangle. The red point is at the other corner of the rectangle. And we want that rectangle to be perfectly matched, almost as though we have a mirror image over here. And in that, the blue vertex would be at one corner of this black rectangle, and this black point would be at the other corner of this black rectangle, and these rectangles are perfect mirror images of each other. Now, of course, my drawing might be off, so the scale might be off, but I think you get the idea. So we have therefore successfully drawn 2 points in addition to the vertex. Yeah, sometimes it doesn't stick, so let me get rid of this. And we're just going to plot that again. I'm not sure how to fix that situation. So there's another point right there. And we could draw a parabola right there. And for future reference, we could sort of take note of the fact that the coordinates of the vertex are negative 1.5 and 0.5. And the reason why it might be worth our time to label that is because the whole point of graphing this at this point is to find the range, because that's what we're being asked right now. Determine the range. So we are attempting to find the range. In other words, what is the set of all y values that is represented on this parabola? Well, that's what we're going to find out. Clearly, the lowest y value is at the vertex. And if we want to know what is that y value, all we need to do is take note of the coordinates of the vertex. The y-coordinate of the vertex is 0.5. So therefore, we know that the lowest y value on this parabola is 0.5, and the highest value is everything up into the positive infinity range. So that's all we need to know with regards to the range. Using interval notation, we have positive 0.5 right here, and then we've got positive infinity right there. And as usual, we have already satisfied I, which says graph the parabola on the coordinate plane given above. Well, of course, we just did that. So we're done.